Okay, we are going to talk about isomerism. We are going to talk about isomerism. Organic compounds exhibit what we call isomerism. As I was saying, isomerism is the existence of organic compounds with the same molecular formula but different structural formula. Of course, we must know that there's a difference between molecular formula and the structural formula. The molecular formula is just a general representation of an compound, whereas the structural formula exhibits different bonds and also the structure of the compound, the way it is. And we are saying that compounds that exhibit isomerism, compounds which have the same molecular formula but different structural formula, we are calling them isomers. We are calling them isomers. And we are saying that we have two classes of isomerism: structural isomerism and stereo isomerism. So we are going to begin with structural isomerism. Okay, now let's look at structural isomerism. We are saying for structural isomerism, it's a type of isomerism which shows the sequence in which the atoms in the molecule are bonded or linked. So structural isomerism is more specific with how the atoms and the bonds are linked together. So the isomerism exhibited here can be very clearly shown by the links and the bonds in the compound. And we are saying it has three classes. The first one is chain isomerism, we have position isomerism, and we also have functional isomerism. And we're going to talk about all of them, but we are going to begin now with chain isomerism. We are saying chain isomerism, it is a style of isomerism in which compounds, they have the same molecular formula, but the difference in the structure formula is due to the different arrangement of the carbon chain, or you can call it the skeleton of the compound. So the difference here in this case is the arrangement of the atoms in the compound in form of chains, as we are going to see in the examples. Okay, now we're going to look at different functional groups, different compounds which exhibit chain isomerism. An example, I can bring C4H10. C4H10. This is a molecular formula of alkanes. Where in this case the number of carbon atoms is 4. And I'm going to show you how chain isomerism comes in. So the first one I can exhibit in form of, I'm going to create a chain that has 4 carbon atoms. Remember we said each carbon must have 4 bonds. Each carbon must have 4 bonds. So I'm creating 4 bonds here for each. And then I put hydrogen everywhere, and then it will become like this.
So
to become like this. Okay, so it will become CH3, CH2, CH2, CH3. However, we can change the chain. You can change the chain by bringing this CH3 and replacing it on carbon number 2 here. We are going to replace one of the hydrogens here with a CH3, and then it will become CH3, CH. One of the hydrogens, I'm replacing it with the CH3, this one, and then I'll put this hydrogen here, and it will become CH3. When you look at this and this, they are all C4H10, but their structures are different because of the difference in the chain. You look at this one is straight, however this one has a branch, but all of them are C4H10. Even if we want to name this one, we'll just call it butane. We'll call it butane. However, this one cannot be butane. It is, when you look at the longest chain, has three carbon atoms. That means it is a propane, but it has a branch, and this branch is a methyl group. and it is of carbon number 2 if you count from this side or if you count from this side. Carbon number 1, carbon number 2. So we say 2-methyl propane. 2-methyl propane. 2-methyl propane. I think you can see that they belong to the same homologous series. They have the same functional group, but the chain is different. That's what we call chain isomerism. Okay, if I can represent this one in this format so that I can show you how bonding takes place. In that case, we have 3 carbon atoms on the main chain. There are 3 carbon atoms. I have created the fourth carbon. I'm creating it and I'm putting it on position number 3. Remember what I said, every carbon atom must have 4 bonds. So I create 4 bonds here. This one already has 3, so I've given it the 4th. This one also has 1, so I give it 3. This one I also give it 3. So I just put hydrogen everywhere. So that is how I am able to come up with 2-methyl propane. I also want to illustrate this kind of chain isomerism using another example, if you will allow me. Okay, I'm going to use C5. Remember, we are using alkanes, and we say the alkanes are the general formula CnH2n plus 2. So I'm using N as 5, so that will be C5. This will be 2 times 5, that is 10, plus 2, that is 12. So it will be H12. So I want to look at different isomers that can come from this molecular formula. We said the first one, you can just create a long chain, and that will just become, maybe I can first relate it like this. I'm creating 5 chains, carbon atoms. So I give this one H3, I give this one H2, I give this one H2, I give this one H2, and this one H3. I give that one H3, and this one we call it pentane. I can change the carbon chain by bringing this CH3 and replacing it on carbon number 2. Let's try that one and see. So we'll have carbon. So it means now the longest chain will have 4 carbon atoms. The 5th, I am bringing it on carbon number 2. So I put here CH3. This one, since one hydrogen has been replaced by a carbon, I will remain only 1 hydrogen. Here we have CH2, and this hydrogen that has been replaced will come here. It will become CH3. Of course, this one will come as CH3. Now, if you are going to name this, you're going to see the longest chain has 4 carbon atoms. That means it is a butane. But the methyl group is attached to carbon number 2. So we shall call it 2-methyl butane. 2-methyl butane. Why do we say butane? Because for an alkane with 4 carbon atoms, it is called butane. With 5 carbon atoms, it is called pentane. But of course, the molecular formula is the same for both compounds. Then we can also have another scenario where this methyl group comes and replaces this remaining hydrogen on carbon number 2. That will become C. It will be C, and then C, and then C. This one is already here. And then this methyl group, I can put it up here. So it comes as CH3, even here, CH3. Of course, the hydrogen which was here is going to add to this hydrogen, and they become 3. So I'll have CH3 there, and also here, CH3. It is still C5H12, but now the chain has changed. And if I'm going to name this, of course, the longest chain has 3 carbon atoms. That means it is a propane, but it has 2 branches now, and both branches are methyl groups. But they are still on carbon number 2. So I'll call the first one is on position number 2. The second one is also on position number 2. Since both of them are methyls, I will use the word di. Di means 2. So I'll call it dimethyl. Dimethyl. Since the longest chain has 3 carbon atoms, it will become a propane. Make sure when you are naming, you do not separate the words. You do not separate the words. In fact, even here, let me not separate the word because it is one word. It is one word. But between a number and a letter, there must be a dash. Even here, I put a dash, or you can call it a slash. Okay, now let's look at the second structural isomerism, which we are calling position isomerism. We are saying in this case, the molecular formula is the same, but the structure formula is different because of the position of the substituent groups or the position of the functional groups on the carbon skeleton. In this case, I'm going to use an example of maybe an alcohol. And an alcohol I can use, remember we say the alcohols are of general formula CN H2N plus 1 OH. H2N plus 1 OH. So I can begin with when N is 3. That would be C3. This is our first example. C3 H. That would be 2 times 3. That is 6 plus 1, 7. H7, then OH. H7OH. So if I am to come up with isomers, of course there are 3 carbon atoms. As you can see, there are 3 carbon atoms. So I can create here a CH3, I create here a CH2, I create here a CH2 again, and then I attach OH on that carbon. The last carbon, which can also be the first carbon. And the name here, it shall be, of course, alcohols are derivatives of alkanes, and therefore even the names come from alkanes. Propan, but now it's going to be an alkane, and I have to mention the position of the functional group, which is OH. OH is on carbon number 1, if I count from this side. Remember, when we are naming these compounds, we must make sure the functional group is attached on the carbon with the least number. So if I make this one carbon number 1, this one carbon number 2, this one carbon number 3, the OH is on carbon number 1. So I would say propan 1,1O. Propan 1O. However, this functional group, I can bring it to carbon number 2. And therefore, in that case, I will have C, and then C again. Of course, this will be CH3. This will be CH3. I brought my OH here. And therefore, it means it has replaced one of the hydrogen. We have remained with only one hydrogen. This one is also an alcohol, propanol, but the position of the functional group now is on carbon number 2. If you count from this side, carbon number 1, number 2. So, in that name, that means in our naming, I'll call it propan 2O. Propan 2O. So, position isomerism in this case, what matters most is the position of the functional group on the carbon chain. But the functional group is the same. That means even the chemical properties might be slightly the same because of the similar functional groups. Okay, now the last part on structural isomerism is called functional isomerism. In this case, the molecular formula is the same, but the structural formula is different, and its difference is caused by the different functional groups. So it is very possible for a compound to have the same molecular formula with another, but the functional groups are different. For example, the easiest example I can bring is if I'm going to consider C2H5, in fact, let me call it H6O. This is a molecular formula that is shared by both ethers and alcohols. for carbon with for a compound with 2 carbon atoms. So let me give an example of an alcohol. It will be CH3, CH2OH. And when you look at the hydrogens, they are 5. The hydrogens are 5, right? They are 6. In fact, they are 6. The carbons, they are 2. 1 oxygen. But it can also be an ether. It can also be an ether. An ether, the functional group for the ether is there must be carbon atoms attached to the oxygen. So the oxygen shares 2 carbon atoms. That is the functional group for ether. So I can create here CH3 and then also here CH3. CH3. Of course, this one my naming is called ethanol. On the other hand, this is not ethanol. This is called, when you look at this one, this is a derivative of an alcohol. I can call it methoxy because it comes from methanol, methoxy. Then this is a derivative of an alkane, methane. So it becomes methoxy, methane, methoxy, 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 methane, methoxy, methane. There are many other there are many other examples of molecular formulas that can relate alcohols and ethers. The other group of homologous series that share the same molecular formula can be carboxylic acids and esters. Carboxylic acids and esters. A good example I can bring when you look at I can use propanoic acid. Propanoic acid is CH3 CH2 COOH. When you look at that one, what would the molecular formula be? Of course, the molecular formula is C3. This is 5 plus 1, that is 6, H6O2. H6O2, when you look at it like that. But now you can also form an ester from this. Of course, an ester, the functional group of an ester is you need a carbon with a double bond on oxygen and then another oxygen here connecting a carbon. This is the functional group of an ester. So in that case, I can create here CH3 and even behind I create CH3. Still it will be carbon, there are 3, oxygen, there are 2, hydrogen, there are 6. So this one is called propanoic acid. Propanoic acid. But when you look at this one is a derivative of carboxylic acid. It's just that one of the hydrogen has been replaced by a methyl group. So that methyl group I can call it methyl. This one is a carboxylic acid of carbon, 2 carbon atoms, and it will be called ethanoic acid. But since it has a substituent, we shall call it ethanoate. So it shall be methyl ethanoate. There are many other classes of compounds which end up sharing the same molecular formula, but their functional groups are different. But for now, we can just stop at those ones.